usual. So speaking of homework, if you were thinking to yourself, I don't have anything fun to do this weekend. I'm looking for suggestions. Do I have something for you? Not only could you do homework 3 that is due on Monday, but you could get started on 4 and 5, which I put up yesterday. So I know some of you are interested in working ahead, and I am totally cool with that. I have not changed very much relative to last year. I tweaked homework 4 a little bit, so if you watch the videos from last year, you'll have to change what you do in the 3rd section, but if you want, we'll be going over this stuff within the next few weeks as well. So just to give you the option to keep working forward as much as you want. But the topic for today, then, homework 3. Did you want to ask any questions for the group? Yeah, my current grade is not good. Yeah, this is person 1, last name ONE, ID number 11111111. I have a series of dummy logins that I can use to open the thing up without showing anyone's grades. But yeah, person 1 is behind the 8 ball right now. All right, Alex, did you have questions, or did you want to just talk about that in office hours? Because that's an option as well.
I did. Getting the section 2 of the homework set up what was tripping me up. But if no one else had a similar issue, we can move on, and I can just hit you up during office hours. I want to be respectful of other folks' time as well.
Well, that's a very nice offer. Do you want to ask me quickly what happened in section 2?
Yeah, so in section 2, what I'm trying to do is oh goodness gracious. So I'm trying to run, so if I'm looking at your example, I copied lines 111 through 119, and I tried to modify that so that, it said the prediction fit count, and I figured if we were censored at 7 and we wanted counts for 4 and 10, it would be predict fit count 4, please, parenthesis, please count 7 equals -3, intercept 1, please count 7, space -3.
Yes, that seems reasonable.
Yeah, and then I did the same thing with 10, inserting 10 where the 4 and stuff was. But then when I try to run that line of code, okay, well, I just pulled up a new log, so it doesn't tell me what's going on, but it doesn't do anything. I don't get an error message, but nothing's happening.
Okay.
So
I have a hypothesis. So those statements that you just described are estimate statements. They would be placed below the model line that describes what is being predicted by what, but they have to go before the lines run and quit. And so I'm guessing that you may not have run those together as a set. If you just did run, it's going to be hanging. It looks like nothing happened, and there'll be like words at the top that say it's still going. You need the quit also.
Yes, so I have the run quit title at the bottom of all of that. And I tried to run it all together.
Okay, then it may be something else that I'll have to look at with you directly. Make sure that you're rerunning all of the steps to import the data and create your predictor variables each time, because there's no memory within the system. So there's that.
Yes, as well. And I very well may not have, I might have missed a space or added an extra something somewhere along the line.
Semicolons, yeah, little stuff like that can trip up SAS. So, but yes, yeah, well, office hours would be fine.
Sweet.
The other class does not have any homework due right now, so office hours are still going to be relatively empty. So anyone is welcome to stop by with that. Any other questions I can answer about homework 3 while we're on the topic? No? Everyone's looking down. eating, thinking. We're good? Okay, carry on eating and thinking. I am pro eating, pro thinking. No one wants to be hungry while looking at all of this stuff. So we can look at the beach and I can ask you my normal question. What do you remember from last time? We have a bit of a Sesame Street vibe. This episode is brought to you by the letter F.
I was going to say, I remember the letter F, but
Yeah.
here we are.
What does F refer to? What is it used for?
Isn't it like a significance test?
It is a distribution that we use to do significance testing with. Yep.
And it's squared.
It is squared. That's important to remember because F will always be positive. So the sign does not tell you anything about the set of the direction of a relationship. Why is it squared?
Because a slope could be negative and you don't want those to cancel out.
Yeah, so how many slopes does an F test?
One. 2 or multiple.
Multiple, yeah. So
there we go.
Yeah, you can use F for just one, and it would be the same thing as the T value for that slope. And T is signed, but if you squared T, you'd get F. But F is used for testing more than one slope at a time. That's why it has to be squared, so that if you have a positive slope and a negative slope, they don't somehow counteract each other. So F takes into account not only the estimates of the slope and their standard errors, but also the relationship of those standard errors, because what one slope is going to be related to what the other is. So it's a more complicated process under the hood, but conceptually it's the same idea as testing jointly whether a set of slopes is different than 0. And why would we want to do that? Any ideas?
Can you say the question one more time? Oh, sorry. Go ahead.
Well, I don't know for sure, but I'm thinking maybe that it allows us to test for more than, like, it allows us to increase the number of, I don't know the right word. All I can think of is factors, but I know that's definitely not it.
Predictors or fixed effects, fixed slopes.
Okay, so like it allows us to work with more of those.
So yeah. That's the general idea, is that when the question you're trying to answer involves more than one slope. So the specific context that we looked at was the idea of a predictor variable that consists of 3 groups. If you have a predictor variable with 3 groups, how many possible mean differences are there amongst those 3 groups? This is a finger question. You can keep chewing and answer. Across the 3 groups, how many possible differences? Yeah, we got 2 votes here. So if we go group 1 and group 2, group 1 and group 3, and there's also 2 and 3. So there's 3 possible differences, but what I think you are answering is how many slopes do you need? That's 2. Yeah, because you can get the third as a linear combination. So if you have 3 groups, then one of the groups is going to have its mean given by an intercept. Each of the other groups is going to have its mean given as an increment to that reference group that comes from a slope. So 2 slopes and the intercept combine to give you all 3 means and all 3 mean differences. So if I wanted to know if this predictor is related to an outcome, that's still the idea of a bivariate relationship like we did in the last unit. But it's a bivariate relationship that takes 2 slopes to fully describe it. So we want to link those 2 slopes together to get a test as to whether or not that grouping variable is related to the outcome variable. And F is a way to put them together. So it's the F test for the models, what we started talking about, which in this case is the same thing as saying the F test just for that predictor, because in our example so far, only one predictor is in the model, the 2 slopes that it takes to differentiate the 3 groups. Okay. I think that's the main point. Sums of squares. Do you remember that? The words, at least. I'm not expecting you to memorize formulas. Remember, I promised that at the beginning of the semester, and it holds true. Sums of squares is the idea of information contained in an outcome variable, and we have to understand how much information that is in reference to how many slopes it took to get it. That's sums of squares versus degrees of freedom. So can I give you a real world analogy that might help with this a little bit? Would that be better? Okay. So it's my mom's birthday in a couple of weeks. We're going to see her and my dad in Omaha. My mom and I do not often agree on things, but one of the things that we do agree on is a love of the store Kohl's. So there's Kohl's across the Midwest. I am in head to toe Kohl's in most days of the week, right? It's all about athleisure right now for my teaching wardrobe during the pandemic. And one of the things about Kohl's is that you will never pay full price. If you pay full price at Kohl's, you are doing it wrong. Because between the Kohl's cash that you get for buying things and the fact that everything is always on sale, and then there's always another promo code that you can put in, like, there is no actual money at Kohl's. It's like monopoly money. You have no idea until you get to the register how much things are actually going to cost. But my mom is very proud of her Kohl's savvy negotiation skills with all of these mechanisms for savings. And so she'll come and call me on the phone and say things like, oh, I went to Kohl's this weekend and guess what I got? I got your dad some socks, and I found a new top, and I found this cutest shirt for Huey, and guess how much I paid? I only paid $5 for all of it, right? She's very proud of like getting this whole sack of stuff for $5. So she's excited about the concept of having gotten a deal. It's not a deal to buy 3 things. It's a deal to buy 3 things for $5. So in me trying to judge how excited I should be about her deal, it's not enough for me to know the contents of her shopping bag. I gotta know how much money it cost. That's sums of squares for the model. That's her shopping bag. What did you get? You put these predictors in the model. What did they buy you in terms of prediction of an outcome? How many slopes did it take to get to that bag? How much money did you spend? That's numerator degrees of freedom. So if I had, let's say that I had my $5 bag, but then I went and splurged, right? I went over to like the fancy section, like the J.Lo clothing line that's at Kohl's, where the jeans are slightly more expensive. And let's say that I, pretended I was 22 for a minute and bought myself some skinny jeans. Never going to happen, but this is my story and I can live in it. Well, those jeans might be $40. So then it's like, oh, well, I have my 3 things for $5, but my jeans for $40. Is it still a good deal to buy 4 things for $45? Like, I don't know. That's not a great deal anymore. So you have to think about, what did you get in terms of the result of the prediction, but how expensive was it? If you accounted for, say, 10% of the variance in an outcome with 1 slope, that's great. If you accounted for 10% of the variance in an outcome with 10 slopes, it's like, that's not so great. So the whole logic of sums of squares and degrees of freedom is a weighting system by which to judge how effective your model is at predicting an outcome relative to how complex it is. So sums of squares for the model is like, what did you get? How much information was captured by your model predictors per slope it took to get it? That's sums of squares model. And since I'm talking about those terms, let me pull up a table or two. 1 second while the slides load. Let's see here. This table. This is slide 14. So we're trying to break down this first row here. So if I have my amount of information captured by the model per slope it took to get it, per degree of freedom for the numerator, that gives me the result of something called mean square model. Or that's kind of like stuff per dollar as a ratio. It's the idea of quantifying a deal. But then the other half of it is, well, how much is left over? In Kohl's, like, there's going to be a lot of stuff left over. There's a lot of money I could have spent. So that's the other half of the equation is like, okay, what did you leave on the shelves? a joke that my dad would usually say when he sees us come home with the shopping bags. Did you leave anything there in the store? Ha ha ha. It's like, be quiet, Dad. You got new socks out of the deal, right? And you didn't even ask. It's not even your birthday. Yes, at some point in your life, you start buying things like underwear, t-shirts, and socks as birthday presents. I haven't gotten there quite yet, but I have a feeling that day is coming. But anywho, residual is like what's left in the store. So how much information is left to be predicted in my outcome? What are the things I didn't buy? How much would it have taken to buy all of that? So what's left? How far off is your outcome from what it was predicted by the model? And then how many slopes could I have still added? Then that is residual variance. That's the idea of sort of unit of information left over per degree of freedom for the denominator. So numerator is based on the number of slopes, k-1 because 1 is for the intercept that we don't count. Denominator is based on the number of fixed effects, sample size minus the number of fixed effects. So mean square residual then is the term that I'm asking you for in your assignments, because that is like the VIN identification for your vehicle. You know the model's right if you have the right mean square error. Okay, how we doing? I get my second vaccination sometime soon. I'm hoping to go to Kohl's for real sometime in the near future. Not just pick something up in the parking lot and have them put it in my trunk, but actually wander through Kohl's and see what I can find. Dare to dream. So the idea of the total amount of information in your outcome minus what's left over divided by the total, that's our friend R square. Yes, I've been warned about feeling like crap. My arm hurt after the first one, and I'll have to see how the second goes. But if I can shop again, I will take it, right? I have small dreams. So R square, we talked about as well. That's the effect size that goes with the F. So F is a significance test. It tells you whether or not the amount of outcome variance that's been predicted by the model is significantly greater than 0. And I'm phrasing it as greater than 0 because it can't go less than 0. The worst you can do is no variance explained. So these synonyms, by the way, I will use interchangeably. Outcome variance that is explained or predicted or captured. Like the idea of some of the unknown variation across these people is now known because of predictors. That's model. R square tells us what proportion of variance in the outcome is now known because of our predictors, has been purchased, so to speak. And you can also think of it as the square of the correlation between the y that you actually have in your data and the y that's predicted by the model, y hat. So how well the model predicts the outcome squared is R square. You can think of it either way. So these two things go together. F tells you up or down whether or not the amount of prediction that your predictors have gotten you is significant, and it's per slope, and then R square is an effect size for that comparison. Okay, questions or comments on any of that? Not yet? Not yet. Okay, I'll take it. All right, so we looked at pictures of F. F looks a lot like chi-square. The difference is that chi-square, which is also squared, does not have denominator degrees of freedom. But it does have numerator degrees of freedom. So you can use chi-square to look at contingency tables. Technically speaking, you could use F as well, but that's not what typically happens. And then we were reviewing all the letters and how they relate to each other. So now you've learned all of the different test statistics that are most commonly used. If you're testing one thing, like one slope, and you do it paying attention to your sample size, that's what T is for. So we use T for Pearson correlation, we use T for individual slopes, we use T for Spearman correlation, we use T for testing a sample mean against a population mean, lots of instances of T. Z is if you do that same stuff without paying attention to denominator degrees of freedom. So that presupposes that you have a large enough sample that it doesn't matter. And what large enough is kind of depends on the context. So you don't tend to see z as much in the models that we're talking about. F then is t's cousin. If you're only testing one thing, the t test statistic for that one thing squared is f. Which reminds me, I haven't turned on the thing that tells me about fish sticks yet. There we go. And now I have to block it. Okay. So f then tells us multiple slopes at the same time, whether or not they significantly contribute to the model, and tests overall sort of sets of prediction. Chi-square would do the same thing without denominator degrees of freedom. But the same logic in terms of how you would talk about it, if your test statistic returns a p-value that's less than 0.05, you would call it significant, meaning it is unlikely to have observed those slopes if the null hypothesis were true. Typically speaking, the null hypothesis is 0, but it doesn't have to be. And I think that's where we left off, was about here-ish. Does that sound right? Okay.
Hoffman, could you go over the why it says t squared if 1 more time?
The if one refers to numerator degrees of freedom, which is the number of slopes being tested.
Okay, so if it was a larger number, would it become like a cubed or a different power?
They're not equivalent anymore.
Okay.
So T is like a univariate distribution. F would be a multivariate extension of it, in terms of what is being what goes into it. So they're only how do I say this? T squared is F only if you're testing one slope. Otherwise, there's no direct correspondence. Maybe? Not quite?
I still don't quite understand, but I will look it up in my own time.
Fair enough. So maybe this will help, actually. The idea of T versus F and R versus R squared. So if you only have one predictor, like in homework 3, for instance, if you have a model that looks like this, relative to the empty model, you would have added this beta 1 slope for the effect of x, because in the empty model, you would have already had a fixed intercept, you would have already had a residual for each person. So we test whether or not beta 1 is different than the null hypothesis, which is usually 0, from a t-test. So we have the estimate for the slope minus the null hypothesis for what it was supposed to be, divided by its standard error. That thing is t. So if all you have in the model is this one slope, if you take that t and square it, you get the same thing as the f for the model that you would have gotten from this table. So if you only have one slope in the model, the test of that slope is the same thing as the test of the model. It is a 1-to-1 correspondence, which is why I said we didn't have to pay attention to the table yet in the last unit. Likewise, if you only have one slope, you can convert that unstandardized slope, which is in units, back to a Pearson correlation as a measure of effect size. So the standardized version of the slope, standardized meaning if you converted x to have a mean of 0 and a variance of 1, and if you converted y to have a mean of 0 and a variance of 1, and then put them in your model, the slope that you got back would be the Pearson correlation. So the slope is telling you the exact same thing as the Pearson correlation. It is a linear relationship between the two variables. The difference is that beta 1 is in units of y per units of x. So inches, pounds, scores, whatever it is. Whereas correlation is always a standardized measure that ranges from -1 to 1. But in this case, if I took that Pearson correlation that describes the slope in standardized units and squared it, that is the same thing as the model R square. So if there's only one slope, the test of that one slope is equivalent to the test of the model. You don't have to do any extra steps. Whereas with two fixed slopes, it is not the same thing to test each of the slopes as it is to test them jointly, because the slopes are related to each other. So in this context, if I have, for instance, a 3-category variable as a predictor, you told me before we only need 2 slopes to be able to capture all possible mean differences. Then F is telling us to what extent beta 1 and beta 2 together result in a significant prediction of the outcome. So to what extent is the y hat that's given by this model correlated with the actual y? If I take that correlation and square it, that's my model R square, and F is the significance test of that R square. 2 slopes work together. And each, the extent to which these 2 slopes work together, it's information that they capture relative to the number of slopes. So sums of squares model divided by the number of slopes gets you to mean square model, which is the idea of the deal from Coles from before. All right. So this is what it would look like, for instance, in the table that I'll show you in SAS and Stata using these numbers. We have sums of squares for the model. So how much better did we do than just giving each person the same guess as to what their outcome is, giving each person the sample mean for the outcome? How much better did we do? How many slopes did it take to get to that level of prediction? There's the end result. Then how much is still left over relative to how many slopes we could have added? That gives us mean square residual. And then the ratio of these 2 numbers is F. So F is a ratio of what you know over what you don't, each of those things being scaled by how many slopes it would have taken to know. How many it took to explain the model, how many you could still add. And in practice, this is the reporting format that I'm going to have you practice in your homeworks, because this is a nearly universal way of describing these results. You would report F in parentheses each degree of freedom. So degree of freedom for the numerator is how many slopes you're testing as part of your F. Degrees of freedom for denominator is number of slopes you could have added, so sample size minus the number of fixed effects, is whatever your F is. Then MSE, mean square error as it's referred to, that's mean square residual. You can call it either way. And then the p-value that goes with that F. Do you know the reason why it's these particular numbers that you're supposed to report? Has anyone ever taught you that before? No. The reason is that with those values, you can work your way backwards and get every single number on this table. If I know F and I know mean square residual, then I can figure out what mean square model is. If I know how many slopes went into it, I can get to SS model and so on. And actually that was a homework that I had to do once in intro stat, I remember. Question, would that be a Mad Lib type question on the homework? Which question? I think I missed the context for that.
Oh, you said that how we report it. I was just thinking, like, would it be one of those where we're selecting the drop down? Okay.
Yep, what you're going to practice about 18 more times before the end of the semester is the values are going to be auto-populated from your answers, and the drop-down menu is going to have the letters. So is this one the F? Is this one the P? Is this one the R square? Is this one the MSE? Is this one something else? Yep. So you should be able to recognize what the value refers to because you got it correct up above, and then just tie it into a reporting format that summarizes the information in this table. Yep. All right. Yeah. One more thing, by the way, R square has a cousin that I'd like you to have heard about, adjusted R square. So for the same reason that Pearson correlation sometimes has an adjustment suggested for it based on small sample sizes, there is an analog to adjusted R square that's used in small samples in regression. You can ask for it in SAS Proc Reg, stands for regression instead of GLM. State of Regress gives it to you as well. And I have never once been asked for this in a manuscript. Never once. But just in case, just in case somebody says you should be reporting adjusted R-square instead, you can say, yes, okay, fine, I'll put that in. So in our case, it makes very little difference. The unadjusted R-square was 0.103 from our example. The adjusted version is 0.101. Either way, what this R-square tells us is that roughly 10% of the total variability in income is predicted by that 3-category working class predictor. So 10% explained, 90% unexplained in the residual. Yeah, effect size. Yeah, that's the next piece. So, how are we doing? Okay-ish? They need like a thumb that's sideways, right? Like, it's okay. Hanging in there. All right, effect size. So the idea of effect size, being able to describe the strength of a relationship in an absolute metric that is directly interpretable no matter what the units are of the variables. That's the goal of an effect size. So you know R already, and we've talked about D, but just to remind you, D is standardized mean differences. For a categorical predictor like this, a D is a more intuitive effect size than an R because it talks about how different two groups are in standard deviation units. There are lots of this variance of D. People have come along and tweaked what goes into the denominator and added extensions for various circumstances. So you may see other variants of this, but D as a concept is very common, standardized mean difference. And I, in my example, have created D's out of the t-test statistic that shows up on your output. So if you have a t and you have your denominator degrees of freedom, you can convert that back into a D. And by the way, you can get an R out of that instead. So the reason that I put this up here is that power analyses. Do you remember this idea from a few weeks ago? Trying to compute or anticipate statistical power. So the question that I want to make you aware of is power for what? That should always be the first question after someone says, can you help me compute power? Or someone tells you that you need to compute a power analysis. Power for what? So even in this relatively small scale analysis, power for what is an important question. So there are 3 different group differences that we might be interested in, as well as an omnibus R-square effect size. So for instance, if I take my beta 1 slope, it was estimated as 8.8, meaning that people who are in the middle group rated themselves had higher income by 8.8 than people who rated themselves in the lower group. Standard error was 1. That translates into a t of 8.82. I can get from a t to a d of 0.65. So in standard deviation units, the middle group is higher than the low group by 0.65. So a little over half a standard deviation. From the power tables that we looked at before, there's power for R and there's power for D. The line that corresponds to power of 0.80 for an effect size about this size means that I need to have at least 45 people per group to have an 80% chance of detecting a D of 0.65 as significantly different than 0. So that's not so bad, right? 45 people per group. What about the second one here, lower versus upper? Large difference, but a large standard error, in part because there's not a lot of people in the upper group. Well, now I have a D of only 0.27. So the lower group and the upper group are only a third of a standard deviation apart, because there's a lot more noise in estimating the mean for the upper group, because there's very few people in the upper group. Well, now to get adequate power to detect an effect size that small, I need 175 people for each group. For the third slope, that's a linear combination, the difference of the non-reference groups, I need 2,102 people to hit that one. And if I phrase a research question instead, just What is my power to see whether or not working group as a predictor is related to income? Then for the model, the power for my R square, if I unsquare it and put it back into an R metric, then power is 0.80 if I have at least 85 people. So those are 4 very different answers as to how big my sample needs to be to have power. Because it's power for what? So this is tricky in practice to figure out what you're trying to power and making sure that you have enough power for the thing you care about, because all of this would be of interest potentially in looking at how a categorical predictor relates to an outcome. So effect sizes for specific contrast as well as for the overall model, things that you would want to consider and report. All right, and then we're at the summary stage. So putting it back together again, and then I'll show you how to do this in SAS and Stata. If you only have one fixed slope in the model, the test of that slope is the same thing as the test of the model. The t for that slope, if you square it, is your f for the model. The standardized version of that slope, which is your Pearson correlation, squared is your model R square. If you have more than one slope in the model, such as when you're testing differences across 3 groups in this example, then you would still have a significance test for each slope, as well as any linear combinations of those slopes, but then you would also have a separate F test for their joint contribution in predicting an outcome, the effect size for which is an R square. So that's it for that. And do you remember what this is called, by the way, if you have a quantitative outcome and you have a categorical predictor? Nope. That's fine. You don't have to remember. I'll tell you. I'm waiting to see if anybody does remember, though. A categorical predictor of a quantitative outcome, otherwise known as ANOVA. That's what this is. This is analysis of variance. In particular, this is a one-way analysis of variance because I have one predictor. Can you guess what it would be called if I have 2 categorical predictors?
A supernova.
No, but it should be called that. ANCOVA is if I have a categorical predictor and a quantitative predictor. But if I have 2 categorical predictors, it's a 2-way ANOVA as opposed to a 1-way ANOVA. And that model implies interaction terms as well. So, but I like supernova instead. Let's go with that. ANCOVA? I can't fit the C in there. I got to work on that one, but I like it. So do you want to see how to do this stuff? Yeah! May as well. We're all here. All right, example 4 then. We'll do the first part of this, and after we go through this, you'll be able to do the section 1 of your homework 4 as well. Although I will warn you, that one is a little trickier because it has 4 groups. So the next formative assessment that we go over will be foreshadowing how that code will need to look different to account for 4 groups as a predictor rather than 3. So this is still playing with the same data, general social survey data. Basically, I'm going to walk you through the code that resulted in the numbers in the PowerPoint presentation. So how did I get all of those estimates? How did I build the variables to do those things? So SAS, first step, always read in your data. Note that this is the extra part that is needed if your data reside in some place other than the H drive. So you can ask the virtual desktop to connect to your local drives, but then you have to have this prefix on there. So I'm using my Dropbox folder here. Proc import for the Excel data as usual. Proc format to add some labeling conventions. So there's 2 different categorical predictors that will be featured in this example. One of them is the working class variable that we've been talking about. So 1 means lower class, 2 means middle class, and 3 means upper class. And another one is the ordinal happiness measure that we saw in example 2. That will make a repeat appearance towards the end of this example. I'm reading in the data, adding labels so that we know what all of our variables mean, adding the labeling conventions via a format statement, and then selecting complete cases for all of the variables as part of this analysis. So you won't need to worry about this in your homework, but you will need to worry about it in your life. So I include this here. And then Stata folks, similar process. Tell it where your stuff is. Import the Excel spreadsheet where the data are stored. Here are the labeling conventions for the categorical predictors. Adding the labels, adding the labeling conventions, and then dropping cases that have missing data. Okay, so any questions on the setup or the variables as part of the story?
Lisa, just a quick, like the part that you just went through, the only like, just that last part you mentioned about drop if, that's all like pre-written. That's not necessarily something that we're overtly changing in the
Correct.
initial of the data. Okay.
This is the part that I give you as a starter syntax each time you have a homework, and the only part that you have to change is the path to where your file is.
File or file state. Yeah. Okay, great. Just one. Thanks.
Yep. So I will highlight the parts that you will have to do in terms of additional code, and that's coming when it's relevant for each model. So, yep. Okay, so then first step, descriptive information. We're going to be predicting income. Here is descriptives for that variable using proc means and using summarize. So the mean of income is 17.3 in $1,000. The total variance in income is 190. Those numbers are going to show up in our empty model results. So going back over that just to review that from before. Here's a picture of what it looks like. So here's a histogram. And I have a note here that this is the marginal distribution of income. What the model is assuming, though, with respect to normality is about the residuals. We don't yet have a model, so we don't yet have residuals. So we won't know, just by looking at it, whether or not our results are going to be plausibly correct for a general linear model with respect to the standard errors. But we will see that. So empty model, first step. So I use this primarily as a pedagogical tool. I feel like it's helpful to understand where R square comes from, because the empty model returns as much variability as there is in your outcome variable as a baseline. So proc GLM is what we're still using, regress and stata. Income is the name of our Y outcome variable. An empty model has no predictors, so it's blank right there before the slash. And in stata, there's no other word before the comma, so just income is being predicted. Each of these models by default includes the fixed intercept beta 0, so that's not something you have to reference in the code, it just shows up automatically. And here is the table in SAS. If you want to see the output in stata, I have that online as well, but since it looks pretty much the same for these cases, I didn't print it in each case, in each class. So in SAS, at this point, the only thing that's in the model is the mean. So when you estimate an empty model, it treats the model as just the mean of the variable, and so this F is telling us that the mean of income is not 0. So not terribly informative because it's not a predictive model yet. So mean square error 190, that's all of the variance there is to be had in income. The baseline in terms of a predictive outcome for each person is just the fixed intercept. So if you don't know anything else about a person, your best guess for their outcome is just the sample mean of the outcome. That's the 17. So our job then is to take that 17 and customize it for each person based on a distinct set of predictor values. So in this example, I think we're going to have 3 or 4 different models in total, different predictive models. We'll just do the one for working class today. So the categorical predictor that we've been working with, work class, I can get descriptive statistics summarizing it using procfreak or using tabulate. So in life, you would want to do this for any variable that is categorical to ascertain just how many categories there are and how many people there are in each category. So in this case, there's 20 people in category 3, which is not a lot, but it is at least some variability. You may run into problems in models where there's only one or two people in certain categories trying to ask for differences relative to that category. So that may be a case in which you need to either kick out those people or collapse categories that don't have enough people to actually be included. So running descriptives on categorical variables is important to try to dictate how they would then be included in the model. So in this case, I'm going to leave it as is, 3 groups, and then here's the code that we went over in the PowerPoints to do the dummy coding. So dummy coding as a phrase is the process of creating new predictor variables. So we are converting a single column, which is 1, 2, 3, into 2 new columns that have either 0 values or 1 values, and we're assigning those values in a particular way that creates an interpretation of what the slopes for those predictors are then going to mean. So you control the interpretation by assigning the pattern of 0s and 1s. So for instance, in your homework, you have a 4 group variable, and I'm going to say make group 1 the reference. So if I said that to you, make group 1 the reference, what am I telling you to do with respect to how the variables are to be created using dummy coding? So make group 1 the reference. How do you do that?
Group 1 would be 0 and the others would be 1.
Group 1 would be 0 for what specifically? Because you're correct.
I'm not sure.
So 0 on one new variable that we're creating, or all the new variables?
All of them.
Column.
Each column, yes. So in the SAS code, that happens here, and in the Stata code, it happens here. So because I have 3 groups, I need 2 new columns. In your homework, you are going to have 4 groups. How many new columns are you going to need? 3. So if I say make group 1 the reference, I mean 0 them out across all the new columns. Because the reference is another way of saying make them the intercept. The intercept is when all predictors are 0. So if I 0 them out across all the new columns, then the fixed intercept in the model becomes the predicted outcome mean for that group specifically, because that's when all the predictors are 0. Okay, does that make sense?
Lisa, can you say more about what you mean by 0 them out across all? So like, so what I think I'm getting a little tripped up on is like, I remember in our, the example with the columns, like I know the first line and it matches with what you have here, right, is 0, 0. But then like, are you saying whenever 1 shows up in the columns, it needs to be the 0?
Whenever you're referring to group 1, all values of the columns that you're making need to be 0.
Okay.
So see if I can paste this onto here. We'll see if it'll let me. Okay. Not very effectively, but hang on 1 second. I ruined my handout. Let's paste it as a picture. And then we'll change the layout so that I can move it around and make it little. Because yeah, I think it's helpful to have like a conceptual understanding of what the code is trying to do, which is this right here. There, that's a little better. You get the live action version of me making these handouts. It's all about pasting things in and moving them around. So, okay, now please ask your question again to make sure that I'm answering it correctly.
No, for sure. So when you said assign 0, you said something along the lines of like assign 0 across all of them or something. Is it whenever we're referring to So like in this example, the low being the 0, anytime we're putting a low in one of the column boxes, it needs to be the 0. Am I misinterpreting that?
Uh, I'm not sure if we're saying it the same way, but I think you're right. It's whenever we are telling the program what to do for the first group, we're telling them that all of the new variables to be created take on 0 values.
Okay.
And so that's filling in the first row of this little table here.
Mm-hmm. So how does that impact then? Is that what you're talking about then, the first row, or does it impact any of the other rows of the column? Maybe that's where I'm confused.
At this point, the 2 new columns are first created as blanks.
Okay.
And then conditionally based on the value of this other column. So for those cases that have a 1, take those blank columns and fill in zeros instead.
Okay.
And so then here's the blank columns in Stata, and here's the fill in the zeros instead in Stata as well.
Okay.
And so then for the people who have a 2, now fill in a 1 for the first column and fill in a 0 for the second.
Okay.
And then for the people who have a 3, so that gets you to the second row in the table. For people that have a 3, fill in a 0 and then a 1.
Okay.
And so then the net result, when these 2 columns appear together, is that they have the desired interpretation of the first new column, the L versus M, holds the difference of how the middle group differs from the low group. Because it's 1 versus 0. But then you're like, wait a minute, but this is 0 too, so how doesn't it get confused? Because then that's where this variable kicks in. So the first variable lumps together these 2 zeros. The second variable's job is to separate them. So when it's all fit back together again with these 2 predictors both in the model simultaneously, the intercept is the expected outcome when all my predictors are 0. That has to be then what the outcome is for working class equals 1. The first column is going to tell me how the middle group differs from the low group. And the second column is going to tell me how the upper group differs from the low group. Okay, does that help at all?
Yeah, I think it does. I think I'm just trying to make sure what I'm seeing on the code actually makes sense to my brain based on what we talked about. So I think I'm chewing on it. I'm getting there.
Okay. Would it help or hurt to show alternative ways of coding this? It would mean different things. Because I sort of I like seeing extensions of that, but then I don't want to be confusing.
Yeah, I don't know for me. I think at this point I am starting to understand what you meant by the 0 and how this is very much connected, essentially the same as the column. So I don't want to speak for everyone though. Perhaps it might be helpful to someone else.
If I gave you an instruction that said make the third group the reference, how would this pattern have to change?
So would you need to have it would change based on the combinations of the zeros and ones, I think. So the third would be 0 0.
Yep. So if I change this to 0, that would be the first step in making sure the third group is my reference. And this one would be okay. This one would have to become a 1. But then the labels wouldn't make any sense. Because what the first column would represent would be 3 versus 2 and 3 versus 1.
So would you need to change the order of them too?
Not necessarily. I would just change the names of the new variables to accurately convey what they mean then. So like
Okay.
the L versus M is a specific example because that's what this variable means to me.
Mm-hmm.
I would have to rename it. It would be U versus M and U versus L is what they would mean.
Like upper versus middle and okay.
And what if you did something like this? What would happen in your results, do you think?
You'd get the same, like it wouldn't know the difference between the work class 1 and the work class 3.
Yeah, it would lump these two together, and then it would actually give you a row of dots for this variable instead of any sort of numbers. Why do you think that would be? Is this a variable?
I'm gonna say no.
Yeah, if everybody is a 0, what is this? What's the opposite of a variable?
A constant.
A constant, yeah. Can you have a constant relate to something else? Nope.
No.
So it'll be like, and give you dots where there should be answers. So that is to say, when you're going through your homework, if you get dots where you're supposed to have something, something's wrong in the coding. So let me put this back to the way it was so that I don't accidentally mess this up for future use. So then in homework, if I said that you had 4 groups, you told me we need 3 slopes, right? So that would mean adding another set of these in each line, so 3 new columns, as well as another line that says what to do if it's group 4. So extending the table down 1 row and over 1 column. So it would be like a 4 by 3 in that case. So that's what I'm hoping you'll be able to try to figure out on your own, and we'll talk about it as one of the quiz questions too, to try and help you troubleshoot that. Okay, so then stated code looks exactly the same, it's just backwards. So the conditionality is at the end of the statement, and what happens in terms of replacing the 0s and 1s comes first, but it's otherwise does the same thing. So other questions on the variables going into this? Okay. So this is the thing that you would need to do in your homework, by the way, if I haven't made that clear. This is something that you'll have to figure out how to get the coding right for your 4 variables. Then here's how the model tells me what the mean is going to be for each group on my outcome variable and what the mean differences are between each pair of groups on my outcome variable. So here's my model. Directly, I'm going to get a beta 0, I'm going to get a beta 1, I'm going to get a beta 2. So if I fill in the 0s and 1s for each of these new columns that I've created as a function of which group I'm trying to get a prediction for, it would look like this. So the patterns of 0s and 1s in this set of 3 lines here, those directly match the pattern of 0s and 1s that I just built up here. So beta 0 is going to directly become the lower group mean. The other 2 means you're going to have to ask for as a linear combination. So in your homework, for when you go through this in number 4, I'll ask you for the mean for each group, but some of them are going to be things you'll have to ask for separately, and some of them will be things that get spit out automatically. Likewise, mean differences across the groups. In this case, 2 of them are spit out automatically, and the third is a linear combination. So the code then down here, these estimate statements in SAS and these lincom statements in Stata, they are doing these equations for you. the trick to understanding how these statements work is remembering that when you type a word like intercept or the name of a predictor, what you are referring to is not the variable. You are referring to its fixed effect as estimated by the model. So when I type intercept, I am asking it to internally remember what beta 0 the intercept was estimated to be and to use that number in this equation. So this says I need beta 0 times 1 plus beta 1 times 0 plus beta 2 times 0. So it's filling in these equations. And the differences. I need beta 1 times 1. I need beta 2 times 0. So the only one you technically need to ask for is this one, which is beta 1 times minus 1, and beta 2 times 1, which works out to be beta 2 minus beta 1 up here. So all in told, you get one mean directly and any mean differences relative to the reference group directly. Anything else you have to ask for separately as a linear combination. However, I even in my own analyses, not when I'm teaching, I write them all out like this. I am in the habit of doing that. So I'm writing out the statements that are given directly as model parameters in addition to those given as linear combinations, because this is my trail of breadcrumbs to remember how this model works and what each of these terms means. When you go through the trouble of setting all of this up, you want to leave yourself a nice way of remembering what it means that you don't have to like rethink it through the next time you open this up. Have you ever had the experience of like doing something and then coming back to it like 6 months, a year later, and you're like, I have no recollection of having done all of this, but this is my writing, or this is, this is my handwriting, this is my code. This is save yourself from yourself, right? Write out exactly what this means. So this creates a table of output where thing it is, number, answer, thing it is, answer, that is very well labeled, makes it a lot easier to share that table and to remind yourself how the model is parameterized. So then same thing happens in Stata with the exception of the word const instead of intercept, which refers to the fixed intercept. And the multiplication of the values of the predictors and the addition of the linear combinations is explicit. Okay. So questions on any of these statements? Not yet. All right, then results. So here's the table that I had told you to skip over before, but now we don't have to skip it anymore because you know what's in here. So the first piece of output then is telling you about your model as a whole. So why, for instance, is there a 2 here? What does 2 tell me?
I'm going to guess the number of slopes.
Yes, it does. It is also known as what? Did I hear degrees of freedom?
Degrees of freedom.
Which one?
Yeah.
There's
Numerator.
2. Did you both say it? Say it again.
I said denominator.
That's the numerator.
Oh.
Would you like to, either of you like to change your answer? Because it's one or the other.
Jen, how sure do you feel? Because I feel.
I feel 50% sure.
Oh no. I don't know. I'm not sure. I was just. I think you might be right.
So here's a mnemonic for you, right? If you were to view this as a ratio, the thing on top is the numerator, the thing on the bottom is the denominator. It's in the same order in the table.
Numerator.
It's numerator.
Way to go, Jen.
Yep.
Numerator.
Degrees
Okay.
of freedom numerator is the number of slopes being tested in your model. So then that makes this thing, 731, denominator degrees of freedom. Yep. and that's based on your total sample size. So corrected total here, the 733, that's because there are 734 people in this analysis. From the empty model, my best guess as to what any person's outcome would be is the sample mean. I had to spend 1 degree of freedom to get to that point. So that's why it's corrected total, because it's minus the 1 for the mean. I spent 2 more to do this model, which means I have 731 slopes I could have put in this model. If I were to do that, I would have explained all the variance there is to be explained. So then these numbers you don't typically need to pay attention to, but they are quantifying the numerator of what would normally look like a variance equation. They're sums of squares. Sums of squares for the model is how much information we captured by putting group in as a predictor. It is the deviation of each person's predicted outcome minus the mean. So how much more informative the prediction is, squared. Left over, the difference of each person's outcome minus y hat, so the sums of squares of the e's specifically. And if I take that number and divide by 731, I get our friend right here. So that thing, 171 in this case is the residual variance, or mean square error, or amount of information left over. All of the reasons why people may have different incomes that have nothing to do with this predictor variable. So is that a lot? Is that good? 2 ways to think about that. Number 1 is our friend f, and this p-value right next to it goes with f. So f is a ratio. It's a ratio of what you know to what you don't. In this case, we know 42 times as much as we don't know. So that's good. P-value, so is f significant or not significant?
It's significant.
Significant, yeah. By any standard of alpha, yeah, this is less than 0.01. So we'd see an f this big, less than 0.01% of the time, if in reality our model did not predict our outcome, if the slopes as a set were 0. The other thing that goes with that f is right here, is r square. R square is the effect size for the degree of prediction given to us by the model. So this means 10%. We have 10% of the variability in income predicted by this outcome variable. 2 slopes bought us 10%. That is a significant level of prediction. And so then the summary of all of this right here that you would see in a results section is just this much. F, degrees of freedom, is the F value, MSE, residual variance, and then the p-value that goes with the F. Because those numbers allow you to recreate everything else that's here. And then these are the things that you get by default. So this table is what I would call the solution for fixed effects. It's not labeled as such in the output, but that's what it becomes in other packages. So it gives you the estimates, standard errors, t-tests, and corresponding p-values for each fixed effect in your model. So fixed effects include intercepts and they include slopes. So the first column is the number, the value of the estimate, the point estimate. The second column is the standard error. So intercepts have standard errors, slopes have standard errors, but they have a similar meaning. Do you remember what standard errors are? Cough, cough, homework question. Concept of a standard error?
How far the slope of the sample is from the slope of the population, or
that would be, yeah, so that would, either of these that would hold for, because these are standard errors of slopes. So how far off on average a sample slope is expected to be from the population slope. Likewise,
intercept.
This one would be for the intercept.
Yeah.
So this number, the 0.62, tells me how far off on average this intercept would be in the sample relative to the population. So standard error in general is a way of indexing the expected inconsistency of an estimated parameter across samples. Everything that gets estimated has a standard error that goes with it. And just like standard deviations, these are unsquared units. So standard deviation talks about how far off a person is from the sample mean. If you square standard deviation, you get variance. These are standard errors that are a higher level of abstraction because they're not talking about people, they're talking about samples. If you were to square these terms, by the way, that is a quantity known as the sampling variance. So that's something you may see in statistics, but it's not commonly something you would see in a data analysis unless it's a quantitative methods article, something like that. And estimate divided by standard error is where these t's come from. So in putting this all together, the sign of these slopes tells you the direction of the relationship. The sign of the slope estimates will match the sign of the t-value. So if it's a positive number, that means as x goes up, y goes up. If it's a negative number, as x goes up, y goes down. As x goes up, in this case means as we move from the reference group to the alternative group. So as x goes up means moving from the low group up to middle, or from the low group to upper. Then one more table. These are the extra parameters that I requested via the estimate statements and the lincom statements. So each group mean has an estimate and a standard error. These p-values you would typically not report because they just tell you whether the mean is different than 0. And then here are the 3 possible differences as well. So this is the only one that I really needed to ask for out of the 3 differences because that's beta 2 minus beta 1. So in this case, based on this one line, how would I describe this result? The slope distinguishing the upper group from the middle group is what? First off, positive or negative? Positive. Significant or not significant?
Not significant.
And where are you looking to tell me that?
At the PR greater than T.
Yeah, that thing right there. That's my probability of observing this result if the null hypothesis is true. P is greater than 0.05, well within expected territory. So putting that all together, p-value is non-significant, slope is positive, the slope is non-significantly positive. And this is what the residuals look like. So relatively more normal than before, but still definitely not exactly normal. And a little bit heteroscedastic. A little more variability in the middle and upper groups than in the low group in residual income. Okay, I think that's it for that. Almost. Standardized slopes. So that's the one thing that we haven't seen yet, is in proc-reg, which is this another procedure in SAS, you can ask using the option STB, standardized betas, to get standardized slopes. In Stata, it's under the regress option, just with the option beta. And that gives you the same exact information, but it gives you this extra column out to the side here. So these are your standardized slopes. They are in standard deviation units where all of the variables have been standardized to mean 0, variance 1. And then D. So I also computed D's for you using that formula from the slides. All right, in words, because I want you to know how to talk about this in life. All right, questions before we wrap up for the day? Okay, then we can go back over any of this you want to next time. Otherwise, keep working on homework 3. Let me know if you need anything. And our office hours at 3:15 if anyone wants to join us. So, all right, have a good weekend. Stay safe.